Well, for this video, we're going to be going over 3.2. This is going to be con continuity. And so, for the first thing that we need to go over when it comes to continuity is a left and right limit. So, from my last video that I talked about with limits with functions, right? When you have a function, right? Here, first, let's just write this down. So, the left and right limit must agree. So, what this means mathematically is what it looks like is the limit as x approaches, say, some arbitrary term c from negative infinity. You denote negative infinity by putting a little negative here, it's here, of, of x needs to be equal to the limit x approaches c from positive infinity, right? We put the little plus sign on the top of it to denote that it's coming from positive infinity. Needs to be equal, right? These two functions need to be equal to each other, right? And then the next thing that we need to know is that the value of f of x at whatever term x, right, it must agree with the left and right limit. Must agree. So, what this looks like mathematically is that f, say, c must be equal to the limit as x approaches c from negative infinity of f of x also needs to be equal to the limit as x approaches c from positive infinity. So pretty much those are the main things that we need to know when it comes to how can a function be continuous. And what it means for a function to be continuous is, say I make a graph here, I should be able to draw the function and not have to pick up my pencil at all. So what this means, say I draw like a little squiggly line here. See how I didn't have to pick it up and there's no gaps in between the function? That means this function would be continuous on whatever interval, whatever from here to here is, right? For a function to not be continuous, what it will look like graphically is that, say I went here, here, but then, oh, it made a jump here, and it looks like this. And you would have a circle here denoting whether it's what the value of the actual function is. So when you have a circle that's fully filled in, that means that that is the actual value of your function at whatever value x this is. But an open circle denotes that that's not the actual value of the function at that value x. And I'll kind of show that a little bit more graphically later on. So let's get into some example problems here. So write this down. Example problems. So the first one we're going to do here, we're going to have f of x, and then we're going to write out a piecewise function here. F of x is going to be equal to 2x cubed minus 3x go plus 1. And here, and then here. And we're going to set this one when x is going to be greater than 1. This one for when x is equal to 1. and then this one when x is going to be greater than 1. So essentially what this is like a piecewise function, right? So what that means is that at different regions of your function, depending on whether you're greater than, less than, or equal to, for in this case, the value 1, your function is going to behave differently, right? So when values less than 1, your function is gonna behave like a cubic function, right? When you're at 1, it's just gonna be 0. And when it looks like you're greater than 1, it's just gonna behave like f of x equaling x, which is like just a line. So what we now need to do here is what we talked about before. We need to check our left and right limit first. So how we begin to start doing that is what we write is the limit as x is this here. As x approaches 1, from let's go with negative infinity to start off with negative infinity of f of x. And so if we go to look back at our piecewise function, when x is less than 1, our function is going to be 2x cubed minus 3x plus 1. Now, like with what I talked about in the previous video, with what I like to call direct substitution, what we're going to be doing here is plugging in 1 into this function, because it looks like I'm able to plug this in, and we're not going to get a determinate form. And if we remember, a determinate form would be, say, if we got 0 over 0, right? So what we're able to do here is say 2 multiplied by 1 cubed minus 3 multiplied by 1 plus 1. And then we put these terms together. We get 2 times 1, 2. Negative 3 times 1, 1 plus 1. And then if we put all that together, we should get 0. And then we need the right limit, or when the limit as x approaches 1 from positive infinity of f of x. And if we go to look back at our piecewise function, we see that when x is greater than 1, we're going to get x. And so just like how we did before, we're going to plug in 1, and we're going to get the limit as x approaches 1 from positive infinity is going to be 1. And then the last step with how we talked about here with proving continuity is that we need to find the value of the function at that value x. And with what I've written out here, our function at the value 1 is 0, right? Because there's no actual x variable term for us to plug in. And so it just says it's 0. So we could state that f of 1 is equal to 0. So now that we have all that, we can now state that, write this out in sentence here, since the limit as x approaches 1 from negative infinity of f of x, and the limit as x approaches 1 from positive infinity of x, both equal 0, we can now state that the limit, oh, here, let me add on one more term here. Since they both equal 0, and then f of 1 is also equal to 0, now we can say that the limit as x approaches 1 of f of x is also going to be equal to 0. So now that we've gone through that, we can now see an example where maybe one part agrees, but another part doesn't. And let's just see what happens there. Example 2. For example 2, we're going to have x is going to equal, let's keep it similar. Let me just manipulate a little bit. Let's go with, yeah, let's stick with x cubed. X cubed minus 3x plus 1. Don't want this to be 0, but let's say it's x plus 1. And then we're still going to have it where this one is going to be less than 1. This one is where x is equal 1. This one is going to be where x is greater than 1. So similarly, look with how we did before, we're going to apply the same stuff. We're going to take the limit as x approaches 1 from negative infinity. And so we see when our function is less than 1, it's going to be 2x cubed minus 3x plus 1. And we just did that in the last problem, so we know that this is going to be 0. And then take the limit as x approaches 1 from positive infinity of f of x. If we look back at our piecewise function, it says it's going to be x plus 1. We plug this in, we get 1 plus 1. So our limit as x approaches 1 from positive infinity of f of x is going to be 2. And then we look here because we want to know what our value of f of x at 1 is. It tells us that f of 1 is going to be equal to 0. And from what we remember from the rules of what it means to be continuous, our left limit and our right limit have to agree. They have to have the same value. And it also has to be continuous. Well, how to explain? The value of the function at that specific x value has to be equal to the left and right limit. And from what we see right here, I highlight it. Our left limit is saying 0. Our value of where x is at 1 is saying 0. But unfortunately, our right limit is saying that it's 2. So what that means is that we cannot say that the function is continuous because there's going to be a jump, kind of like what we talked about here. So say that let's look here, that our value here from the negative that approaches the negative is going to be, say, this top function here, right? But our function at the bottom is behaving like our function from positive infinity, right? So you can kind of see there's this gap here where it jumps. And so I have to pick up my pen in order to fully write out this function, meaning that it cannot be continuous. So for our statement, we would say that f of x is not continuous at x equals 1. And then a couple more key things to know when you're trying to figure out if a function is continuous or not is that all polynomials are going to be continuous. And another thing to remember is that piecewise functions, they can or cannot be continuous. And then we will have to do our 3 tests in order to determine whether a piecewise function would be continuous or not. So just a couple examples just to test and see which ones are continuous or not continuous. And then some are continuous, but just not at certain points. So, for example, let's go with x squared plus 1. X squared plus 1 we know is a polynomial, so continuous all points. But then if we take, say, sine x, and x is also a continuous function, because we know that sine x is just an oscillating function, functioning between 1 and negative 1, right? You go from here, just a little wave back and forth, and that's going to be continuous because I could draw it without picking up my pen. We'll get rid of that. So we'll say that this is continuous at all points. And then if we take the function 1 over x plus 1 multiplied by x minus 3, well, let's see. When we have a fraction like that, we got to remember our denominator cannot be equal to 0, right? So when does our little function here equal 0? Well, that's going to be at -1 and 3. So it's continuous, all values except negative. Here, let me write this. Except when x is equal to -1 or 3. And then the last one that we'll do here is the square root of x. And this one, remember, it's just another function. And then our function here is going to be continuous for all values where x is going to be greater than or equal to 0, right? Because we can't plug in a negative number into our square root function, right? Because that's going to give us imaginary numbers, right? But we can also plug in 0 into the square root function and get 0. And then we know that all numbers, if we plug into a square root function that are positive, we're going to get some type of value, be decimal or not, or whole number. We're still going to get a value, which means that you could draw the square root function without picking up your pen. And so that's all we need to go over with section 3.2 of continuity. So let's just do like a brief overview of what we need to know. So for continuity, in order to prove it, we need to know that our left and right limit agree. And then we also need to know that our value of f of x at whatever value x we're trying to get to is equal to that value, right? And then we also need to know graphically if a function is continuous, then we're able to draw it without picking up our pen. But if you can't draw it and there's a gap, then that means that it's not going to be continuous. Then we went over our examples with piecewise functions, where we have where the function is acting differently depending on different points, whether it be greater than, less than, or equal to whatever value that the problem says, right? And then we saw how to write out full answer for when we say that's continuous, right? We say that since this value is the same as this value with the left limit and the right limit, and it's the same at this value of the function at x, we can now fully say that the limit as x approaches this value is going to be this limit, meaning it's continuous, right? And then we saw examples where we were given a couple different functions and we were able to say where it's continuous, where it's not continuous. And then we also learned that polynomials are always going to be continuous, right? And we also saw with our example problems that piecewise functions can or cannot be continuous based off the left and right limit. And with that, that's all we need to know about 3.2 of continuity, and that's it.